Hello, I'm Umnik. This is the first round 841 with commentary. Let's go. In problem A, we are given an array of numbers. We can take two numbers and replace them with some other numbers. All the numbers should be positive integers, such that the product of those two numbers stays the same. So basically, we can do as many of such operations as possible. So the product of all the numbers should stay the same. So we have to choose n numbers with the same product. And we want to maximize the sum of those numbers. And while in such type of problems, it's usually the best thing to either try to make all of the numbers as close to each other as possible or as far away from each other as possible. And in this case, we can see that if we have just two numbers, x and y, it's better to get 1 and x times y, so we get some xy plus 1. And for many numbers, we can just apply this transformation with first number and all of the other numbers one by one. So in the end, we will get just the product of everything as one number and n minus 1 times number 1. So we have to calculate the product, add n minus 1 to that, and for some reason print 2022 times that. I guess I didn't want the samples to be very obvious. Maybe they will have multiplied by that in all the problems. So in problem B, we have a grid of size n by n, and in the cell ij we have the product of I and j, and we have to choose the path from cell 1 to cell n, only going right and down, and we want to maximize the sum of the numbers we visit. So when I was talking about the first problem, I said that it's usually the best to either make them as far from each other or as close, and in this case, like if the sum is constant and we want to maximize the product, the other way around from which it was in the first problem, we want the numbers to be as close as possible. And let's look at each diagonal, like when I plus j is fixed. We have this grid. We know that we are going only right and down. Let's look at any diagonal, like this one. We can see that we have to visit one cell on this diagonal, and we will visit exactly one cell on this diagonal. Like each time we move to the next diagonal until we reach the finish. So for each diagonal, we can only choose one cell, and we want its value to be maximum if possible. If the grid is filled somehow, it might not be possible to choose all the optimal cells on each diagonal independently and just hope that they will lie on one path. But if they do lie on one path, then their sum is obviously maximum, because like we split our paths in some like independent parts, and in each part we made the best choice, and if it's actually the path, well, good. And in this case, we can see that like we want to stay as close to the middle of each diagonal as possible, so we will like walk like that. It's actually optimal. And so the sum we want to calculate is like 1 times 1 plus 1 times 2 plus 2 times 2 plus 2 times 3, and so on. And in the end we will have n minus 1 times n plus n times n. So the sum is, well, here we have 1 plus sum of k from 1 to n minus 1. We will group the summands like that. So the first summand is k times k plus 1, and the second is k plus 1 squared. Okay, so we will have 2k squared plus 3k plus 1. I mean, it's not pretty, but we can sum it up. We know that like the sum of squares is up to n minus 1 will be n minus 1 times n times 2n minus 1 divided by 6. Sum of k is n minus 1 times n divided by 2, and this is just n minus 1. And so this n plus n times n minus 1 times 4n minus 2 plus 3 plus 9 divided by 6. I want some nice formulas. Let's try to put n there too. So it will be n over 6 times 4n squared plus 3n minus 7 but plus 6. So this looks like 4n plus 1 times n minus 1, I think. It's the other way around. This minus, this plus. Yeah, so minus 1 times 1 will be minus 1. Minus n plus 4n is 3n, and 4n times n is this. So we get n times n plus 1 times 4n minus 1 divided by 6. First multiply by this and then takes remainder. Sure. Whatever you want, guys. Actually, this is divisible by 6, right? So the answer is like integer. Oh, I didn't mess up in the calculations, that's nice. What? Okay. Yeah, just print the actual answer. Cool. So we are given an integer array and we have to find the number of subarrays. Subarray is, yeah, continuous. So that XOR of the numbers has an even number of divisors. Well, that's insane. Like, XOR and divisors have nothing in common. Even number of divisors just means that this number is not a square. And our numbers are up to 200,000. So we will instead calculate how many subarrays are squares, and we will do that by just trying all the squares and calculating the number of subarrays with that XOR for each square. The number of squares is just square root of well, the next power of 2 after this number, which is 2 to the power of 18. And we can do that by going left to right, and well, we will calculate prefix source, and so we will, for each XOR, we will maintain how many times we have seen it, and then when we encounter a new XOR, new prefix XOR, I mean, for a given number, we know what should have been the prefix XOR in the left border to have this number, and so we just look how many times we had that XOR, and yeah, that's it. I don't really like such kind of problems. Like, that's not the worst one, but like when it's clear that XOR has nothing to do with divisors, like you don't have to connect the part. Like, the problem would be exactly the same if it was sum instead of XOR. I guess like we couldn't be using that the numbers are small, but like it's not good. Okay, so the sum of n is bounded by something nice, but I need to clear this array, and if I will do that for every test, that will be too slow, so instead I will be using counters. So we'll do t++, and now all the numbers induced are strictly smaller than t, so if I want to write something down here, I will set use to t, and now I know that that's the correct value. But if I want to read the value, I will first look at used, and if it is smaller than t, then the value that we store here is actually old. That's from the old test case, and so the value is actually 0. And yeah, we are calculating like bad segments, so good segments are all segments minus bad, so I first say that answer is all segments, and then I will say that bad segments are actually bad. So x is my current prefixer used st, and yeah, if used was less than t, then I have to say that thing is actually 0, and now it's one bigger, and now I read the next number, get new prefixer, and now I need to try all the numbers such that their square is up to the 18th, and subtract from answer the number of previously seen prefix sums, such that the XOR with current prefix sum will be the square of this number. This is not correct. If used at equals to t, only then the CNT is correct, otherwise it's 0. In problem D, we have a rectangular grid of numbers, and we want to find the greatest such number L, so that there is a subsquare with side L, so that all the numbers inside that square are at least L. So basically we want to find a subcube. I don't see why I can't just... Obviously we can do binary search and answer, and for a fixed answer we can just try all the squares, and all I have to do is to take minimum on the subsquare. That sounds like 2D sparse table. What's the issue? Like, do I not have enough memory to do this? No, that's not true. Okay, let's do that. That just sounds so simple. Wouldn't expect that from problem D. So we are doing binary search and answer, then trying all the squares with given side, and we should check that all the numbers are greater, well, at least this fixed number. The answer we are checking. For that we will take minimum on that square, and to take a minimum, like on array, we would use sparse table, but we can do the same thing for subsquares. It doesn't work like that for subrectangles. Like we will, how does sparse table work? We take like we precalculate answers for all the segments of length 2 to the power of k, and then cover our query segment with two such segments. How to do the same for 2D grid? Well, we again precalculate the answers for all of the squares with side equal to some power of 2, and then we will cover our query square by 4 such squares, like for each corner. But if we had queries on rectangles, which can be like very long in one dimension but very short in the other, we wouldn't be able to cover it in constant number of squares. So it works only because we only query on squares. But well, it's the case in this problem, so don't see a problem. So yeah, we will actually need like a lot of vectors here, and that might be scary a bit. But should be fine. So it's just like sparse table, but on 2 dimensions. Nothing hard here at all. So now we are doing binary search. Okay, so get min on rectangle. But we know that this rectangle is actually square, so let's just say that it's square. So it's x, y, and d. So k is this, and we need to return min. So shift will be d minus to the power of k. Sparse k xy, sparse k x plus to the power of ky, and oh no, it's plus shift. Yeah, that makes sense. Why did I calculate the shift? That sounds right. But it isn't, apparently. Oh. Okay, that sounds kind of interesting. So we are given n vertices. They are numbered from 1 to n, and there are no edges initially. We want to add exactly m edges. There shouldn't be any self loops or multiple edges between the same pair of vertices. For a given pair of vertices u and v, we can only add an edge of weight GCD uv. And the process in which we are adding the edges is we're choosing an integer k, and then we add exactly k edges, and each should have weight equal to k plus 1. So first of all, that means that we can only add edges with weight at least 2, so only between vertices that are not coprime, but that probably doesn't matter. And for adding these k edges, we will pay k plus 1. Okay, if we are paying for k edges k plus 1 and we want to add exactly m edges, like for basically we are paying 1 for each operation plus 1 for each edge we are adding. So for all edges we will pay m, and then plus 1 for each operation. So we want to do it in the smallest possible number of operations. That makes sense. And the answer is just like m plus the minimum number of operations. And that can be impossible, apparently. Okay, so we do not have to make the graph connected or anything. So So our sequence of operations is just like these numbers we are choosing as k. We want to minimize the number of operations, and like for each weight there is some number of pairs we can connect with that weight. So basically, like for each number g, let's say that like ag is the number of pairs of numbers x, y such that x is strictly smaller than y, and GCD x, y is equal to g. So we will be able to use this, like when we add edges with weight g, we add g minus 1 of them edges. Ag. So the total number of weight g. The total number of edges with this weight will be some, let's call it some number multiplied by g minus 1, and it should be like at most the number of pairs in which we can use this weight. Okay, cool. So we want to minimize sum of bj, having this condition, and also we have the condition that we should add exactly m edges. Okay, so sum of n is actually bounded. Can we just find all AJs? Like, how fast can we find? Okay, that's a simple inclusion-exclusion, right? Like, for how many pairs their GCD is divisible by G? Well, they both should be just divisible by G, and that's it. So that number is n divided by G rounded down times n divided by G minus 1 divided by 2. But that's not AJ. AJ is like this number after we remove all the pairs that have actually greater than GCD. Like the fact that both of those numbers is divisible by G means that the GCD is divisible by G, but that doesn't mean that it is exactly G. So we subtract all the A's for numbers that are greater than G and divisible by G. And so we can calculate this in n log n time. Okay, cool. Now the problem is that we want to get exactly m. But we only can take groups of exactly G minus 1. it feels like just the greedy will work. Just take the biggest number we can. I don't know if it's true. But like, it should be true, right? AJ are non-increasing, it seems. So, like, if we can take some group, but actually the optimal solution doesn't take it, then it should take like some other things, at least two of them. Let's take the biggest of them and move it right, then we should be able to move this thing left. Okay, we will take the leftmost of them and we will move it left. The sum will stay the same. Okay, the size of this group is increased by 1, the size of this group is decreased by 1, so the sum stays the same, and we will either move this one to this, and it will still be a correct solution, because like since we had taken this number, we know that they fit here, but there wasn't taken anything here, so and we know that their number A is at least as big as this one, or we will move this to 1, where like 1 means 1 is 0, and then just remove it, and then it's a better solution. And yeah, we will stop here halfway, but again, there wasn't anyone taken here, and we could take one here, so we could also take one here. Okay. Yeah, when like the stupidest greedy is actually correct, I also don't like that, because like that's bad for people who actually prove their solutions. Yeah, well, why I said that we can do it in analog n, because well, this couple of cycles work in analog n time, and we like, despite that there is an infinite sum kind of, like we know that for all the indices that are greater than n, this is just 0, so we only need to calculate the sum up to like for k up to n divided by g, and this is exactly what I mean here. Well, this is all just standard stuff. Okay, so we will take k groups of this, where k is minimum of m and ai divided by I minus 1. if we couldn't take enough, then it's impossible. And otherwise, that's the answer. It's a cute problem, I will give it that, but yeah, I don't like that just greedy works. Oh yeah, more mass. What? Okay, so if we are looking at some integer array, we want to define a function of this array that, like, for each index we calculate the number of elements that are to the left that are strictly smaller and that are strictly bigger. The position I is good if the numbers before that are strictly greater is greater, strictly greater than the numbers before that are strictly smaller than ai, and fi is the sum of all elements such that their index is good. And now for given n and k, and n is up to 50 and k is very big, we want to find the sum of fa over all arrays in which all the elements are from 1 to k integers. Okay, so like in all of the problems, we want to change the order of summation, so like the answer is the sum over all arrays of f of a, but we know that f of a is just the sum over all indices ai if it is good. So it's like multiplied by 1 if this index is good and 0 otherwise. So like 1 if this is true and 0 otherwise. That's, I want to say Ackermann notation, but I'm not sure. Okay, so and now we change the order of summation. Exchange these two sums. So for all the indexes from 1 to n, well, this is dependent, okay. For like take sum over all arrays of the element on position I if I is good. Okay, so here's our array, here's our position I. What do we care about? We don't care about all of these guys. Each of them just have k possibilities independently, so that just multiplies the number of arrays by k to the power of n minus I if we stick with one indexation. Okay, and about these guys we care like if it is smaller than ai, equal to ai, or strictly greater than ai. and let's say we have x of those, y of those, and z of those. So we know that x plus y plus z is equal to I minus 1. And we want x strictly smaller than z. So what can we try? We can just try x, y, z. That fixes I. And that's like of n cube. Possibilities. And now, like for x, y, z fixed, we want to look at all the arrays that have these parameters, and we want to sum up the value of this thing over them. Well, okay, so how does that look? Well, we will try that value. We want to sum up this value. We want to choose which positions are smaller, equal, or greater. So that's like multinomial coefficient, x plus y plus z factorial divided by x factorial, y factorial, z factorial. And for positions that are smaller and bigger, we have to choose the actual numbers. That is done independent. When we fix that our value is w, we have w minus 1 values for smaller entries, and k minus w for greater entries. And now we have to sum that up. Oh, this is not fun. Oh yeah, and x, y, and z are fixed, and they are fairly small, so like this is just a constant that we can calculate, and this is like some how do you call this thing? Polynomial in W, and when we sum it up to k, it will be a polynomial of k in so we can either like do the operations like on polynomials, then actually like sum up each monomial which can be done, or we can say that the answer is just polynomial in k of some degree, like at most n plus 10 surely, and just calculate that answer for small k and then interpolate and like then substitute k in that polynomial and get the answer. So first of all, I have to check that the answer is actually a polynomial in k, because like we have also k here. But yeah, surely it will be like for each power of w, the coefficient is just a polynomial in k. So when we sum it up, it also a polynomial in k. Then we sum that power of w from 1 to k, it will be also a polynomial in k. And then we sum up the products of polynomials in k. Great. Okay, so now how do we calculate so like the stupid way would be to just try all the values of k, try all the triplets of xyz, and just calculate the sum. How slow is that? We have n cube triplets. We have to try k up to n plus 10, and we have k summands, which is okay if we calculate these things fast, but these things are just powers of a small number in a small power, so we can pre-calculate them and then just take in constant time. And like this sum only depends on x and z actually, so we can calculate like independent of this for fixed x and z, and only then try xyz to calculate this. So this is actually n to the fourth even, not to the fifth. That's great. Okay, let's do that. Okay, so now we have fixed and n and k. We will, oh yeah, at the beginning I need to pre-calculate all the powers. So now for x smaller than z such that their sum is at most n, we will calculate these sums. So we take -1 to the power of x times, oh, I'm not writing it very sure, times k minus w to the power of z times w. We actually don't need to store them. And just try all the y's here. Okay, so now I have to interpolate. I don't care about n anymore, so I can just say, okay, that's will be the degree of my polynomial. Yeah. Get a bit carried away here. I have this all pre-written. I actually have the interpolation pre-written too, but like, what is the fun in that? Okay, so I have multiplied all the x minus I binomials. So now I have to divide by zx minus y. What do we do? I guess I have never wrote interpolation after I switched to this mint type. So like my fingers remember how I wrote it before. Okay, it should be y times. And now, like, take the answer we got when k was equal to I, but we have to divide it by what we get if we substitute I in this thing, which is product of 2 factorials of I and n minus I minus 1, I want to say. But these guys are actually negative, so if n minus I minus 1 is odd, then we need to multiply it by minus 1. And now that is incorrect. What did I forget? I forgot to multiply by k to the power of what's left. It's k to the power of n minus 1 minus x minus y minus z. Still incorrect. So the numbers engaged are not random. That probably means that like this part is correct. Because if I messed anything up here, I would probably get some random garbage. So the problem is more likely to be found here. yeah, for these things, like I'm actually calculating the answer, like yeah, so I'm doing that incorrect. Let's read the statement. The sum of OAI I don't see anything. The number of elements strictly small should be strictly small. Oh, this the guys after I. Okay. Well, that shouldn't change a lot. Like, I still want to fix this. Like, it will be easy to do in n to the fifth. Like, just iterate over x, z, and I. But that's I mean, okay, let's do it in n to the fifth. So it's like strictly smaller before times all the other guys, which is this, and there are I minus x of them. And then we multiply by the number of guys strictly bigger after and guys not strictly bigger also after. That's n minus I minus 1 minus z. And you multiply by us, and then two binomial coefficients. My position is fixed, and I need to choose the positions for smaller before and for greater after. Okay, yeah, that works, but it's n to the fifth, and I am not satisfied with that. It will get accepted, but I want n to the fourth, and like I'm sure it's possible. And actually, like this and this only depends on I, X, and W. This and this only depends on I, Z, and W. So but I only want them paired together. No, that's not good. Yeah, okay. So let's we'll fix I and W, and then like for fixed X, or like for fixed Z, for example, we want Yeah, instead of writing that, I could have just wrote like multiply by this. And just add it straight to answer. I don't need this. Okay. So yeah, let's regroup those things a bit. So it's me times this and times this thing. But like for fixed z, we want to we actually just want sum of like these things over all x's that is strictly smaller than z, and also they should not be greater than I. And we can actually sum only these things and then multiply by all of that. So let's maintain this sum. We will go over all z up to n minus I not inclusive. And we will say like add to n's sum over all x's times w times all of that. And then we should increase sum by this value for newly added x, which is just z. So sum is increased by this thing, but only if it is at most I. Yep, it works, right? Yep. And that's n to the fourth. We have a cycle here, and then cycle, cycle, cycle. That's n to the fourth. Obviously, you shouldn't go for the best complexity in contest. I'm just having fun. That's insane. I'm not the fastest. Okay, thanks for watching. Bye.